Welcome to the course. I hope it will be a lot of fun. This will be online mode, so I will be showing you slides, and then okay, so I will be showing you slides, and then I will write down some derivations if it is needed. Okay, so so this is the content that I want to cover. So who is this? Kunal Chen. Can you please don't move your mouse? Who is this? Kunal Chen is here. I guess I have to. Yeah, you're not supposed to move. Well, the content that I will cover will be very basic stuff. I think these are the things you may have known before, but I will try to recall a few things. In fact, this basic stuff will continue also in the next class on Wednesday. So let us dive into it. So yeah, so we want to look into counting. Counting is a basic task in mathematics. We all know we use it on daily basis, and our objective, let's say, is to tell in a given scenario how many without actually counting. Okay, so we don't want to count things on fingers all the time. Sometimes we want to derive a clever way, formulas and so on to count. Okay, so what are the applications of counting? Well, the number of steps of an algorithm. This is something you may have seen. You count the steps or the operations that you do, and that's a kind of counting. So to understand the complexity of an algorithm. For us, the counting is really important to estimate the probability of occurrence of an event. Okay, so I will define what is probability, I will define what is an event, and so on. You may have seen probability before, but I will not assume that. I'm not supposed to assume that. So in this course, our goal is to understand counting and how to apply them to determine the probabilities of an event. Okay, it can also be used in some proof techniques. Okay, this is something we may have seen before in the discrete structure class. Okay. Okay, like today, so I will start with some very basic stuff. As we know this, we can, I guess, we can predict that this is like some kind of a bone, and then there are some markings on it, and this is one of the oldest mathematical artifact in existence, and it's about 20,000 years old, and arguably it's meant for counting. Okay, so there are markings that one may use to count. Okay, so well, one could also use fingers, I guess. We may have found it later on. But these may be the earlier records of counting. Well, this is a tablet, maybe made of maybe a stone. And then this is supposed to be a multiplication table. Okay, so the first two columns are supposed to be the two numbers that you're going to multiply, and then you're going to get the multiplied result. Okay, so that's what scientists believe. Okay, so this is about 2600 BC. Okay, so it was around so Iraq. Okay, so the current day Iraq. Okay, so let us move on. So this table, as I said, has three columns, and then it's supposed to be a multiplication table. Okay, so that's what the discovery is. And so how do we count? Well, let us say how many numbers are there between 21 and 31. Okay, so Well, it's 11. Okay, so that's very easy. Okay, so in general, we can say how many numbers are there between m and n, where m is less than n. Well, it's m minus n plus 1. So that's the basic formula that we have now. Okay, so remember in the beginning we said we don't really want to do one by one. Okay, we want to derive formulas, and then in this case, this is how it is. Okay, so how many numbers are there between 33 and 67 which are divisible by 4? Okay, so yeah, so in this case, how do we do the counting? Okay, so well, in this case, what we really want is so what is the number greater than 33 and divisible by 4? Okay, so that comes out to be 36. And then we go to the last end and then say which is the number less than 67 and divisible by 4. So this is 64. Okay, and then these are the numbers in between. We know that they are multiples of 4, and then we write this down as 4 times 9. Okay, and then it's like 4 times 16. Okay, now we can count. Then it is like a familiar problem of how many numbers between. There will be a lag on your side when I write. Okay, that's very natural in the lecture. Okay, and we will keep it informal. Okay, so if you have question, you can ask. This is not really like one of those pre-recorded video. This is live video. Feel free to ask. We don't have to be very perfect. Okay, so just ask when you have doubt. Yeah, but
So could you please
don't
add?
ask very. Yeah.
So there's a friend of
Yeah.
mine who's trying to. She isn't added to the teams yet. She has sent you a request. Could you just accept that? She's asking me for that.
Let me see. Okay, because this is like. So what is her name or something? Email or?
Harshita Upadhyay.
I hope it shows up. Okay, so it's showing up here, and then I have invited her. So is she getting the call? Can we confirm? I have invited her.
I'll ask her.
Okay. I hope I'm allowed to invite because this is like centrally managed. So I don't know whether I am allowed to. Okay, so I will move on. I hope. Anyways, like this recording is also there after the lecture. So if she misses, it's not a big deal today. Okay, so don't worry. Okay. Okay. So coming back. Okay. Yeah, so we transform this into our original problem of counting numbers between 9 and 16. Okay, so we know that this is like 16 minus 9 plus 1. Okay, so this is like 7 plus 1 is like, okay, so, oh, okay, so this is like 9, yeah, so 7 plus 1 is 8. Okay, so so these are the numbers we have between 33 and 67 that are divisible by 4. So we can create. I mean, we can generalize stuff. So that's the thing. Okay, all these things are very basic for you, I know, but that's how it is in the first lecture. Okay, so just revise few stuff. Okay, so what is sum rule? Okay, so we will define a sum rule and then some examples on that. Okay, these rules look very trivial in the beginning, but they can be used they are very powerful actually. They can be used in a wide variety of applications, combining with something else, which is product rule and so on. Okay, you may have known these things already using some formulas and so on. So if it's very simple. If there are m objects of the first type and there are n objects of the second type, then there are n plus m objects of the two types, obviously. Right? This is very common sense, right? But that's how we formalize things. So let us see an example of a sum rule. So how many of the pizza or the burger places are, okay? So pizza places are this many. So by places we mean there are restaurants, okay, that makes pizzas, and then there are restaurants that make burgers, okay. In the current scenario, I must say that this may not be a healthy food. So unless it's cooked really well or nutritious or so on, so with all the things going around. But nevertheless, okay, so let us assume that these many restaurants are there for pizza, and these many restaurants are there for burgers. So how many are there for pizzas? Okay, so there are 7. And how many there are for burgers? There are 5. Okay, so when we look into the sum rule, well, m objects of the first type, n objects of the second type. Okay, so this is the first type. Okay, and this is the second type. There are 7 objects of the first type. There are 5 objects of the second type. So now the answer is evident from here. So the answer will be 7 plus 5. So I have 12 ways of going into either a pizza restaurant or a burger restaurant. That's what it says. It's very simple stuff. Okay. Another sum rule example. So this is a little bit extended form. So let us see. Okay, so we are talking about chess here. Okay, chessboard. Okay, a piece stays in the bottom left corner of a chessboard. In one move, it can move 1 step to the right or 1 step up. Okay, how many moves are needed to get to the position on the picture? Okay, in the picture. So this is the scenario. Okay, and this is the piece we are talking about, and this is the end position, and this is the starting position of your piece. And according to this rule, you can move 1 step to the right. Okay, so I said there will be a lag when I'm writing. When I'm writing here, it's very smooth, but what you might see, there will be a lag. Okay, so don't worry about that. It's a live recording. And 1 step to the up. Okay, so this is 1 step. I mean, 1 by 1 it will go, right? It is not allowed to like jump the steps. Okay, so that's the rule. So the question is, how many ways? Okay, how many moves are needed to get to the final destination here? Okay, so this seems to be an application of the sum rule. In the sum rule, we had to have 2 types of objects. In this case, the objects are like the moves that we have. Okay, so we have the right move and we have the up move, right? So this is so how many of these are there? So if I'm going to the right, I have 1, 2, 3. Okay, so 3 possible right moves, and up move, how many I can do? 1, 2, 3, 4, 5. Okay, so I can do 5. Okay, so very simple here. So the answer is now very evident. So it's like 3 plus 5. Okay, so the answer is 3 plus 5, which is 8. Okay, so these many moves I need to reach to the final destination. So this is just an application of the sum rule. Okay, nice. Okay, so this is just, I have written it here that I have worked out. Now we have to make a remark here on when sum rule cannot be used. Okay, so let us see this example. Okay, so count all integers from 1 to 10 that are divisible by 2 or by 3. Okay, so so we can actually list this. Okay, so we are talking about divisible by 2, we are talking about divisible by 3. Okay, so there are 5 numbers that are divisible by 2. So these are 2, 4, 6, 8, 10. Okay, and there are 3 numbers that are divisible by 3, which are 3, 6, 9. Okay, and the question was about counting all the integers from 1 to 10 that are divisible by 2 or by 3. Right. So it looks tempting to apply the sum rule. Okay, so there are 2 objects, right? So one object is divisible by 5. Okay, and another object is divisible by, okay. So if we apply the sum rule, then it will be 5 plus 3, which is 8. Okay, and you can, I know that most of you will be shaking your head and say, well, this is wrong and blah blah. So which is correct? Okay, so is this correct answer? No. Let us count directly. So if we count it directly, then we have 2, 3, 4, 6, 8, 9, 10. These are the numbers divisible by 2 or 3. And if we count, then there are only 7 of them. But our answer is 8 here. Okay. I know most of you will say why, where it's going wrong. And it's going wrong because we have counted the duplicates like this here. So 6 is the duplicate here. 6 is the duplicate. Okay, so that's the thing, right? 6 is the duplicate. We have counted it twice. So from here, what do we learn? Okay, so from here we learn that some rule is not applicable when those two objects have something in common in the sum rule. Okay, so they must be distinct. It's very trivial stuff. So in the rule of sum, no objects would belong to the both types. That's very simple. Okay, now let us bring in a little bit of set theory. I know again this is basic, but let us nevertheless do it. Today you can think of this as a warm-up session today. So it's going to be light. So set theory, as we know, is a tool that we use in mathematics, okay, or even obviously in many other areas to write down the objects we are dealing with. Okay, so objects could be like numbers or whatever you can think of. Okay, so we need to formalize these sum rules and whatever rules that we want to propose in the future. So set is something that we need to write down things very in a concrete way. Set is a collection of things, and it's a unique collection of things. The duplicates get out of the are removed from there. And a more concrete way to say instead of things is the elements. So the elements set is a collection of elements and could be whatever you can imagine. Okay, so depending on what you are trying to study. Okay, so ordering of the elements in set does not matter. Okay, so it does not matter whether I write apple or orange, or I write orange and apple. Okay, really it doesn't. We all know by now. Examples of set theory, for instance, natural numbers. Okay, it is denoted by this. Okay, so if you don't know by now, okay, set of natural number, you write n and then you write a parallel one. Okay, so it's the counting numbers, right? So we start from 1, 2, 3, and that's how we define natural number. In some books they might include 0, but usually those are called whole numbers. Okay, but we won't do that here. Okay, so we will define natural numbers as something number. Extension of the set of natural numbers. Well, we do have 1, 2, 3 here. We include a 0 here, and then we include the negative of those. Okay, so that's the set of integers. Set of natural number, set of rational numbers are fractions of the form p by q, where q is not equal to 0. Okay, so we all know this. Okay, p and q are integers, so p and q are in integers. Okay. And then we define a set of real numbers as rational numbers union. Okay, so rational numbers union. So rationals union irrationals. Okay. Okay, we all know this. Okay, so let us define some notations in case you may not have. You must have seen actually by now. So this is something called closed interval. Okay, so these are brackets, opening brackets, closing brackets. So these are this closed interval because you have these included. Endpoints are included. When the endpoints are included, it's called closed interval. When the endpoints are not included, like here, it's called open interval. So that's why you see the endpoints are not included here. So 2 is not included here in the set, and -1 is not included. Okay, so this is called open interval. Okay. It turns out that they play a very important role in higher mathematics. There are like you may have seen actually, so you may have done real analysis by now. Okay, I see. So you may have been taught about open sets, closed sets, and so on. You may have seen why open interval is needed in the definition of the, let us say, differentiability of a function. Okay, so how do you define differentiability? You will define it around the open set. You can define continuity. So there is a consequence of continuity on which type of sets you are in. Okay, so there are all kind of consequences of the space that you are working with. Okay, and the convergence of the sequences. Okay, it may happen that I may have a sequence. I'm sorry, I'm going a little bit far, but I won't assume too much. Okay, so if you have not done real analysis, don't worry. Okay, you will also get to know about that or revise that. Okay, so if I have a sequence and then that sequence, if I have a domain D and I have an open interval 2, and then if I define a sequence to be 2 plus 1 by n or something, okay? So my hope of this sequence converging in this domain is not a possibility here, because as n tends to infinity, this is converging to 2, but 2 is not in my domain, okay? So if I had taken a closed interval, and if the sequence was converging, then the limit of that sequence is guaranteed to be in the set. Okay, I'm sorry, I'm going a little bit far, but it's just today is just a warm up. Okay, don't worry. If these things are needed, actually these things will be needed. Okay, I must tell you here that probability and statistics course requires a lot from the other courses. You need discrete maths, you need linear algebra. You need real analysis, but the basic of that, as I said, you don't need too much of that. And okay, and then you could have a possibility of an half open set and half. In this case, it's like half open and closed. Okay, so this is like from the left side it's open, so that's why it's called half open and then closed. Okay, so remember not to forget these notations. Okay, so this is called parenthesis. Okay, so you may know by now. Okay, and this is called braces. Okay, so sometimes we mix these things. Okay, so this is called brackets. Okay, so here like opening parenthesis and closing bracket, then we call it half open and half closed. Obviously, I could have the other way also. I could have this way. Okay, so I could have like 3 and then 4. Okay, so this is like half closed open. Okay, so these are notations. So okay, review of step theory. So this is about defining a subset of a set. So we call a set A to be subset of set B if every element of set A is also an element of set B, and it's denoted by A subset B. A subset two sets are equal if A is subset of B and B is subset of A. A set with no elements is called an empty set, and it's denoted by phi. And there is something called universal set. Universal set is the set that could possibly consider all that we want to consider in the context that we are studying. We are studying real number, then the universal. If we are not going to go beyond the real number, then we take universal set to be the real number. Okay, so if we are only studying about fruit, the universal set will be set of all fruits and so on. Okay, so there is nothing like universal set contains everything. We don't do that. Okay, the universal set depends on in the context that we are studying. Okay, so every set is obviously a subset of the universal set. And then there is a concept of countability. Okay, so countability plays a role in defining. So you go from discrete probability to continuous probability. Okay, spaces, right? So that countability. Up to countability, you are in the discrete space. Okay, so the continuous probability spaces you may not have studied so far. You may have already studied discrete. Okay, so in that sense, countability matters here. Okay, so what is a countable set? A set is called countable if I have a bijective function. So this is very important. Bijective function. Okay, from the set S to the set of natural numbers. Okay, so that's so the examples are n and q are countable. Okay, and a set with finite number of elements, it's called a finite set. Okay, this is the definition of finite set. A set which is countable and not finite will be called countably infinite. Okay, so what I will do today is that I will stop here now because it's I guess it's 9:56 in my watch. We will pick up a little bit of speed in the later classes. The recording might stop actually according to the online thing. So it's supposed to be 1 hour class, right? So, oh no, I'm sorry, I'm sorry. Actually, it should go up to 10:30. Sorry. Okay. Okay, I thought it started at 9. Okay, sorry. Okay, we can continue. We have half an hour. Okay. So a set with finite number of elements is called a finite set. And then sometimes we may have like, it's like not really finite, but it's like keeps going, right? So this is how the natural numbers are, right? Okay, this is how natural numbers are. They are not finite, but they like keep going up to infinity, right? So that's why the term countable came. Okay, so when Gödel, or Cantor, sorry. Okay, so when Cantor was studying these sets, right? So earlier people were studying sets and they were saying, okay, there are sets, natural numbers, and then there are sets like real numbers. Okay, so like they wanted, like, what is the like, can we quantify the cardinality of these? Okay, so you can say that, well, both cardinality are infinity, right? But then so it's like the cardinality of n is, in our normal sense, it's infinity, and it's also infinity, but then one infinity is smaller than the other infinity, right? So they wanted to distinguish between this. Okay, so to distinguish that, we need concept of countability. There are sets that can be counted. Okay, so you can list them one by one. You can put a tag. Okay, so you are x1, you are x2, you are x3. I can point fingers and count, and then I know that I will reach to any given element you give me, and I will reach at some point. It may be like in a billion year. Okay, it may be that I will come in billion, but I will come there, and I will count that out. Okay, that's the meaning of countability. And if I can count that out, then it means that I can list them out. Okay, so, but there are numbers like real numbers. They are like so dense. Like if I draw, like, it's not even about dense. Like, I have used the word dense, but then dense is itself a keyword. It's defined in a proper way. Okay, so in topology. Okay, so I should not use things like that. I mean dense in the sense that but dense also, the interesting thing is that if you think about the usual sense, dense, the way we think about denseness, rational numbers are also dense in some sense, right? There are like so many rational numbers between 1 and 2, right? So in that sense, like, there are infinitely many rational numbers between two rational. Okay, so in our usual definition of the dense, we can say that what about rational number, right? But rational numbers are countable. Okay, so it's very intuitive in the beginning, which sets are countable, which sets are not countable. So here I have very compactly here written that Q is countable, right? So natural numbers are countable is very evident, because I can take identity function and then I can map natural number to natural number. Okay, so it's just the identity map that will work for me. Okay, but rational numbers are countable. It's not very evident. Okay, and this is not my job in this class to do this detailed proof, because this is part of the real analysis. But in the discrete structure, I think we did this a little bit, if I remember correctly. But it's very simple even to do it very quickly, right? So you consider the lattice points, right? So you consider the lattice points like this. Okay, so this is like 0, 1, 2, 3, -1, -2, and so on. Okay, so 1, 2, 3. And then you consider the pairs, right? So this is like 2, 1. Okay, so you consider all these pairs. So then the goal here is to identify the P by Q. Okay, obviously you have to do a little bit processing, because there will be duplicates here. Okay, there will be duplicates here. So how do you identify P by Q as P comma Q on the lattice points? Okay, and then I'm going through in a very crude way. Okay, so and then what the way you may count is like you go like this. Okay, like intuitively it's very clear, right? So you can give me any number here, right? So let us say you give me this number. You can say, oh wow, you say that you can count. What about this? I'm here. Okay, so I'm like let us say very far. Okay, so can you count me? Well, the way I'm going, I will count. The only problem is that I'm getting slower and slower, right? Because the area I have to cover is a big one, but eventually I will come there and count it. Okay, that's the intuition behind counting. So we have to do a little bit of processing here. So there are like little bit of duplicates here. We have to remove those duplicates. So we will cross some duplicates, right? So for example, we may have two. We may have this guy, okay, and we may have this guy also. But the rational part corresponding to this is the same. 2 by 4 is the same as 1 by 2. Okay, so this is the pre-processing that I'm talking about that we have to get rid of. Okay, so you get the idea. You are smart enough to just now formulate this. Okay, so what we know for the sets. So for the sets, there are two things now so far: finite and countably infinite. Okay, so this is something you should remember. Either a set could be finite. This is the easiest case we have is finite, or it could be infinite but still countable. So there are ways to deal with that also. Okay, so this still goes into the discrete sense. Okay, so in the definition of discrete probability space, countably infinite will also be allowed. Okay, no problem here. The problem comes when we start talking about real sets of real numbers and so on. And we will see that then we will have to go into continuous, and then that is the reason why we need calculus in this course. Okay, because we will need to. So the probability will be about computing the area and so on. So you may have to do integrations, and sometimes, in fact, once integration is there, differentiation should be useful as well, right? So we will see how differentiation will also be used there. So these are the things we will see. So you will see a lot of maths actually in this course. So that's why I'm trying to go through in a very careful way, revise everything. Okay, the Venn diagram, again, this is a very simple thing. We start learning these things from the 9th class, so no big deal here. The Venn diagrams look like this, in case you don't know by now. Here, S is the universal set. You can think, okay, so this rectangle is the universal set, and then you have some set A inside that. Okay, so universal set, as I said, is the set that you consider depending on the context, which type of objects you want to study, and so on. So Venn diagram shows a pictorial representation of a relationship of the sets in the universal set. Okay, so in this case, for instance, the B set is inside the set A, right? So that's that tells us that B is a subset of A. So this is how this Venn diagram tells us. Okay, then we can talk about the union of two sets is a set containing all the elements that are in A or in B Okay, and it is denoted by A, and then this is like cup set things, right? So A union B. Okay, so for example, I have the set A. Let us say this is containing 1, 2, and set B. This is this, and then this is A union B. Okay, so union can be represented in Venn diagram like this. Okay, so in this case it's like 1, 2, and 3. Okay, so 1 and 2 are in A, and 2 and 3 are in B. Obviously they intersect, and the intersection point is the 2 here. Okay, so but we don't put two times here. Okay, as I said, set is a unique collection. Okay, so we remove the duplicates. We could have 3 2s, but we will take only 1 2 if that is the case. Okay, so similarly we can define union of 3 or more sets. So here is the union of K sets, and these are the notations you should be familiar with. Okay, it's a union of I equal to 1 to K. This is very, in a compact form, we write the union of sets. Okay, so now I have defined union and I've defined countability. Okay, so now this is this is not the cues that you have to do now, but this is something you can try to prove. Okay, so if A and B are countable, then the union, and I'm talking about like it could be like countably infinite. Okay, obviously finite sets are like countable. It's very simple, right? So when we say countable, we usually mean infinite, right? So countably infinite. Both A and B are countably infinite. Then so that A union B is countable. Okay. So it's a matter of counting, right? So I can write this as A1, A2, okay, AK, and so on. It's countably infinite, so it doesn't stop. And then B, I can write this as B1, B2, BK, and so on. Okay, and A is countable. Okay, so A countable. As I said, you may have a lag. When I write here, it's very smooth, so don't worry about that. Okay, so A is countable. So this means that I may have a function f from A to natural number, and f is bijective. Obviously, that's what we need. And B is countable. So this implies that there exists a function g from B to the set of natural number, and g is bijective, obviously. So now your goal is to define a function h, let us say, okay, from A union B, okay, to natural number, or it could be other way also. Since it is bijective, it doesn't matter. You can reverse also to this. Okay. So as we know now, okay, this is just a matter of tagging, right? It's just a matter of tagging now. And processing needed a little bit here, okay, because A and B may have duplicates also, right? So there's nothing like saying that A and B does not have anything in common. But remove the duplicates, we can come up with a subset, okay, which does, okay, and we can work with that. Okay, it doesn't matter. So so the way we can count is simple now. Okay, so for the 1, we can map to A1. Okay, so 2, we can map to B1. Okay, 3, we go back to A set. Okay, so A2. Okay, and 4, we can map to B2. So you see the sequence now, right? So the way we have to define this, okay? So if the natural number is odd, right? So if the natural number is odd, then you define like this, okay? Okay. So if the natural number here that you have is the natural numbers which are odd are mapped to AIs, and then you just have to be careful how to map these indices: 3 to 2, 1 to 1, okay, and 2 to 1, and so on. Okay, so you get the idea of how to do this, right? So A union B countable can be proved. Okay, okay, countable union of countable sets is countable. Okay, since we have shown that the of two countable sets is countable. So A is countable, then A union B is countable. We have shown before. This is a little bit more, okay. So it's like of the sets, okay. So what this is saying is like A1 union A2 union A3 union union AK union, and then this goes on. This is also like infinitely many of the sets A are there, right? Okay, and then we are supposed to prove that this is this thing which is like union of AI. So this is the component that we described before, right? And I go from essentially infinity. Okay, it's like so we are supposed to prove this thing, the infinite union, right? Infinitely many of these unions of these will still remain countable, right? So this may not be very evident, right? Because we are thinking like, oh my God, there are like so many infinite sets are there where we are taking union, and they are like really many of infinite of them, right? So union of this should really not become countable, right? So that's our intuition. Here's that, right? It turns out that it should be countable. Okay, so countable union of countable sets should be countable. And the trick to use here would be induction, our very familiar induction. So induction is typically used for proving results like that. So for any, so if we could show that, so to start with induction, so the base case we know that it will be the union of two, right? So so the statement that we may make is like P2 is the statement that A1 union A2 is countable. Okay, so this is the base case, and if so, there is like if A1 A2 countable. Okay, so so this is like PK is the statement that I'm talking about here is the union over I equal 1 to K, AK is countable. Okay, so I can define a statement PK, which is the union of I equal 1 to K, AK is countable. So this becomes the base case. P2 is countable, and this is proved in the previous previous fact. Okay, and our hypothesis will be that PK is countable. Okay, so PK is true. That is the union of AKs is countable, and then we have to prove that claim is that PK plus 1 is true as well. Okay, so now so PK plus 1 is basically PK union. So that is PK that is P. So that is like union of AK I equal 1 to K union. Okay, so let us make this union of AK. Okay, this is what we have. So AK plus 1, I mean the PK plus 1 statement is like union of I equal 1 to K, and then union of AK plus 1 is countable. This is what we are supposed to prove. Okay, so it is countable. Okay, but then this goes back to the base case, right? So this goes back to the base case because I can choose these as A, I can choose these as B, and the base case is proved to be true. Right? The base case is not something we are assuming, right? So base case is already known to be true, and this is coming from the induction hypothesis. Okay, so it should be true for all K. Okay, and hence the countable union of countable set is countable. Okay. Okay. Other set operations are intersections. So okay, so here it should be intersection. So intersection of a set is a set containing all the elements in A and B. Okay, so and it is denoted by like this A and cap and then B. Okay, for example, here 1, 2 intersected with 2, 3 is 2. If we look into the Venn diagram, then this is the 2 that is in the intersection. Similarly, we define intersection of 3 or more sets as follows. Okay, so that's just the notation here to keep in mind. We define complement of we denote complement of a set by E to the superscript C. Okay, so these are set of all elements in A that are not set of all elements in the universal set, but not in A. Okay, so this is how. So this is the complement. That is okay. Set difference is denoted by like this. Okay, so A minus B. Okay, so this consists of all the elements that are in A, but not in B. Okay, so for example, let us say A is 1, 2, 3, B is 3, 5. Then A minus B is 1, 2, right? So set of all elements that are in A but not in B, right? So we look for what are the elements of B which are here. So the elements of B which are here in A is 3. So that's the thing that we removed. Okay, that's the thing we removed, and that's how we got only those elements of A which are no longer in B. Okay, so 3 was the element which is no longer in B. So that's how there is something called symmetric difference. Okay, so that's like A minus B union B minus A. Okay, So I'm not defining that, but yeah. Okay, so this is the symmetric difference. Okay, so remove anything of A that was in B, and that will be A minus B. Okay, all these things you are familiar. So two sets A and B are mutually exclusive or disjoint if they have no shared element. Okay, so that is when A intersection B is empty, two sets are disjoint, and this is something you will use from time to time in probability. Okay, so something called disjoint events and so on. Okay, we can also define Cartesian product of two sets. Okay, so let us see what it means. Okay, so there are some typo here. So set A consists of elements A1 to AM. Set B consists of elements from B1 to Bn. Then A Cartesian product B. So this is called the Cartesian product B. Are the set of ordered pairs AI Bj. Okay, and union over all Ij. Okay, so obviously I is running from 1 to M. And J is running from 1 to N. Okay, so you take all possible pairs. Okay, you cannot flip these. Okay, you cannot put BI before AI. Okay, if that is the case, then you have to do B cross A. Okay, that's why we call it ordered pair. Okay, so this is the Cartesian product. And what are the examples of Cartesian product? The common examples are something called R2. So this is Cartesian product of two real lines. Okay, the set two. So this is the real line. Okay, on the x-axis, and this is the real line on the y-axis. If we take the Cartesian products and all possible pairs, okay, then this will fill the whole R2 space. Okay, so this is the R2 space. Okay, I hope things are streaming well. Okay, then there is something called partition of a set. A collection of non-empty sets A1 to this is partition of a set A if they're disjoint and their union is A. Okay, so this is one possible partition of the set S. Okay, so here S is the union of A1 union A2 union A3 union A4. Okay, so this is called partitioning of the set. Okay, and they must be disjoint. So the A1 intersection mutually disjoint, right? So A1 intersection A2 must be empty. Okay, A2 intersection A3 must be empty, and so on. Okay, so all the sets in the partition must be disjoint, and their union must be whole of A. Okay, so in this case, used S here. Okay, so the set we are talking about is S here. Okay, and then there are De Morgan's law for any set A1 to AN. We have this De Morgan's law that we have seen in the discrete maths class set theory. So complement of the union is intersection of the complements, and complement of the intersection is union of the complements. Okay, and then we have distributive laws. This is something if you don't recall, then you should know these things by now. Rule of sum using set length. So remember earlier we talked about sum rule, and now the sum rule can be written using set theory. That's how set theory is helpful, because we can write things in a more rigorous, concrete way. So if there is a set A with k elements, and then there is set B with n elements that do not have okay, common elements, then the union will have n plus k elements. Very trivial stuff, but that's the sum rule. Okay, so they don't have anything in common, and hence the union, the cardinality of the union will be cardinality of A plus cardinality of B. This is how the set theory helps, right? We can write things in a concrete way. So can we apply the rule of sum when A and B intersect as follows? So remember in the beginning we said that, okay, sum rule, there is a problem if there is an intersection or there are common elements between the two types. Okay, so this is the first type, this is the second type. If they do intersect, then this means that they have a common element, and that's when sum rule will not apply. That's in the language of set theory. Okay, so so if we do apply the sum rule here, then we will count the this thing twice, right? So if we what we are interested in is cardinality of A union B, and if we do this, then this overlapping region is counted both 2 times in A. Okay, so this is counted here, and this is also counted here. So we need to subtract that. So this is something you already know. Okay, remove the common part because it has been counted twice. So remove just the one of these. Okay, one of the intersection part. Okay, so that's the inclusion exclusion principle. And again, like you can prove these results. Okay. Okay. So let us see some more applications of sum rule. So count all the integers from 1 to 10 that are divisible by 2 or by. Okay. So let us count all the numbers from 1 to 10. Again, numbers which are divisible by 2 or 3. Again, there is a problem. And then sum rule can be applied. Actually, this example we did already, right? I don't know why I'm doing this again. Okay. Let us see the sum rule again in a different context. So suppose there are several. So basically look at the graph. Okay. And there is a source and there is a sink. Okay. The question is how many different ways are there to go from S to T. Okay, so how many so the question is like, can we apply the sum rule here? Okay, so so the counting here we can do recursively, right? So the first thing is like we can ask how many ways I can go from S to this guy. So it's like only one possibility, right? How many ways I can go from S to this one? Okay, so how many ways to reach here from S? There's like two ways to reach here. So this is like we are using the recursive thing, right? So how many ways? So we can add. Okay, so this is 1 plus 2 is like 3. So, and then how many ways we can come? There is one arrow coming from this, right? So this is like 1. Okay, so how many ways to, so 3 plus 2, 5, and then it's 6. Okay, so I hope we didn't do any mistakes so far. So it's like 3, and then this is 1, and then from here it's like 2 plus 1, 3, 6. Right? I hope it's correct. Okay. So so again, like sum rule can be used, but it's just that you have to use recursively. Now there is something called product rule. Okay, so product rule says the following: if there are k objects of the first type and there are n objects of the second type, then there are k times n pair of objects. Okay, so there are k times n pair of objects. So the product rule, let us see an example here. Okay, so the product rule, let us see an example. So there are k objects of the first type and there are n objects of the second type. Okay, so how many objects are there of the type pizza here? Okay, there are 4. And how many objects are there of the soda type? Okay, so 3. Okay, so according to the product rule, then how many pairs of object we can form? It will be 4 times 3, which is 12. Okay, so these many options are there. So these are the possible options. If I can look into the pairs, then these are the possible options, which are 12, right? Okay. We can write this product rule using set theory again. If there is a finite set A and a finite set B, okay, then there are cardinality of A times cardinality of B pair of objects, the first from A and the second from B. Okay, so that's the product rule in terms of sets. Okay, so applications of the product rule, for instance, how many different 5-symbol passwords can be created using lowercase Latin letters only? To answer, before we answer this question, let us see here how many different 1-letter passwords are possible. Okay, how many different 1-letter passwords are possible? So 1-letter passwords, how many ways I can put numbers here? 26 ways. Very simple. How about 2 letters? How many ways? 26 ways here, 26 ways here. So 26 squared. How many different 3-letter passwords are possible? Again, the same logic, right? So it's like 26 cubed. Now using this pattern, can we answer the question? Well, it's very simple now. Okay, so we have like 5 places. Each places we can have 26, 26, 26, right? 26, the 26 to the 5, right? So we can have so many 5-symbol passwords. Okay, so So can be generalized this. Okay. So I think I have like 2 minutes left, or I guess. So, okay, so I will just finish with this. Okay, so I'm almost done. So suppose we have a set of n symbols, then how many different sequences of length k we can form out of this? So this is just a application of the previous rule, right? So, so we have k, and then we have to fill with n symbols, right? So n possibilities, right? So n to the k, done, right? So this is what is described here. Okay. Okay. So I guess I will stop here because it's these timings are very strict. I hope things went well. This video will be recorded and it will be there. So in case there was an issue, please let me know. Okay, please do let me know, because this online thing is something we are doing with, sometimes networks may not be nice and so on. So do let me know about your feedback, and I hope to see you on Wednesday